Thanks for joining me today for this session, which is about integrating S3 and Lambda to create a flexible pattern at the core of serverless applications. My name is James Bezic, and I'm a developer advocate with the AWS Serverless team. We only have 30 minutes today, and this is a 300-level session, so I'm going to cover a few different areas. First, I'll cover the main benefits of building serverless applications using the S3 to Lambda pattern. Then I'll show how to automate the deployment when you build solutions that combine code with infrastructure using the AWS Serverless Application Model, also known as SAM. And for most of the session, I'll talk about a variety of use cases where this pattern can be helpful in building business applications. Throughout the slides, there are links to code where you can deploy examples to explore the concepts further. And at the very end, I'll wrap up with a quick summary of the main points. Before we start with looking at the benefits of the S3 to Lambda pattern, it's worth recapping how this integration works. When objects are created, copied, or deleted in S3, S3 can invoke a Lambda function. It can also do this when a Glacier restore is initiated or completed, also on delete when an item's either permanently deleted or just the delete marker is created, and also when an object is lost in reduced redundancy storage. You configure notification settings on a bucket and grant S3 permissions to invoke a function based upon resource-based permission policies. This asynchronously invokes the Lambda function with an event containing details about the object. And you can match on an object key prefix or suffix as well. Only a single Lambda function is typically triggered this way, especially if you need overlapping prefixes or suffix, but you can also use SNS for fanout instead if needed. So what are the characteristics of these services? Well, for S3, this is object-based. It provides 11 nines of durability, and it has virtually limitless storage. It provides lifecycle management, so you can expire objects or move storage tiers based upon rules. It supports encryption and also provides fine-grained permission models for your applications. For Lambda, this is our functions as a service offering at the heart of the AWS Serverless portfolio. It provides duration-based billing, so you're charged for the length of time that you use the service. You can configure memory, which also controls the amount of virtual CPU available to your code. It supports a number of runtimes, including Node, Python, .NET, Go, and Java. And you can also bring in your own runtimes too. We have customers using PHP and even COBOL. It's stateless, it scales automatically, and it's event-driven. So the reason for highlighting these services' main capabilities and features is that it's important when you combine these services. You get the benefits of both services in a single application. If you've worked with Lambda in any way or run through any tutorials, you've probably come across this example. This solution allows you to optimize images stored in S3 at the point where they're written to the bucket. It uses a Lambda function to process the image to optimize the size and the quality. Let me just walk through this example quickly. An S3 bucket exists to receive images, and then a Lambda function is configured to resize or optimize an image using a library like ImageMagick. The S3 bucket triggers the Lambda function, and after the image operation, the final image is then stored in the second S3 bucket. There are many implementations of this available online for different runtimes using different image libraries. It's an often quoted example, so I won't retread it extensively here, but it does show some of the important ideas behind serverless. So why not just resize images using EC2? You could easily install a script on an EC2 instance to crawl images in buckets and process them in a similar fashion. Well, the image resizing example highlights some of the key benefits of approaching this problem serverlessly. The first is scalability. We bring compute to the data. What do I mean by that? Well, it's less obvious when you observe the image resizer function operating on a single image, but if thousands of images arrive all at the same time, you can see how Lambda responds and scales up. From the developer's perspective, you only write the code that would manipulate a single file, and you don't need to worry about how it works at scale. It also shows how event-driven architectures work in distributed systems. Lambda is inactive until triggered by an event. So in this case, the arrival of a new object in an S3 bucket. This event invokes the Lambda function with a JSON payload describing what just happened. The Lambda function performs its work and then it terminates. In terms of flow, the control is orchestrated by the event happening. Third, you pay for value. Not only are you paying for the image resize, both in the storage in S3 and the invocation cost of the Lambda, but this makes the cost very easily attributable. If you're building a SaaS product, for example, or an application for your clients, it's then easy to calculate the cost by customer. The fourth is security. Between the access control lists of the objects in the bucket policy, and the IAM policies of the function, if configured with the principles of least privilege, it can create a highly secure approach to the problem with minimal ongoing security maintenance. Finally, it's serverless, so there's no operating systems to patch, no instances to scale, and no infrastructure to manage. Now, although the image resizer function is interesting and certainly useful, it's really only the beginning of the things you can do when you attach a function to an S3 event. This is a good time to introduce SAM, the Serverless Application Model. SAM is also the mascot for our service. As you start to develop serverless applications, you'll be creating infrastructure, Lambda functions, and triggers invoking Lambda functions, like the triggers from S3. SAM is a CloudFormation extension designed to make the serverless application deployment that much easier. All of the solutions I'll be discussing integrate with S3 and Lambda and other services. You can set these up manually in the console, of course, but SAM simplifies the deployment and configuration, so you can deploy the entire solution using simple commands from a CLI. For all of the examples in this session, I'll provide you with a GitHub repo with code that you can deploy to your AWS account. These all use SAM, and there are instructions in each repo that show you how to deploy each template. So on the left is an example SAM template. It's just YAML, and each section has a specific role to play. The first section simply tells CloudFormation that it needs to transform this template. This is standard boilerplate that you see in every template. The parameters section allows you to provide input parameters for your deployments. In this example, there is a bucket name provided, and it uses a type of string, and it's called S3 Auto Translation. The resources section defines the AWS resources in the application. The first resource listed here is an S3 bucket, and this says that the new bucket should have the name defined earlier in the parameters section. Next is a Lambda function, as shown by the type AWS Serverless function. The properties here define the configuration of the function. It specifies that the function uses node 12 and has 128 megabytes of RAM. You can also specify a managed IAM policy, S3 CRUD policy used here, using the S3 bucket name input parameter. This can help you apply granular permissions to your functions by using simple statements. It also specifies the code URI, that's the location of the code, and what the handler is called. A little further down, the events section describes how the Lambda function will be invoked. Remember, Lambda functions are always triggered by an event. SAM lets you define that event here. In this case, it sets up an S3 event in the bucket named in the parameters section. This will fire on any S3 object created event, and these happen when any new objects are created. There's also a filter on the key suffix. This specifies that then the trigger only works for object keys that end in .txt and nothing else. Once you have a complete SAM template, you then run the SAM deploy command using the AWS CLI. That converts the YAML on the left to the resources on the right. In this case, it creates the S3 bucket, the Lambda function, and the integration. Once deployed, this Lambda function will always be invoked when a new object is stored with a suffix of .txt. You can also deploy Dynamodb tables, API gateway endpoints, event bridge rules, really almost any type of resource within the AWS cloud. So now I have 5 example applications that show how the S3 to Lambda integration can work to solve common challenges. I'll cover each use case fairly quickly, but there are additional resources on the slides that you can explore with blogs explaining the architectures and full repos with working applications. In the first example, I'll show you how you can create an automated translation solution. This allows you to automatically translate objects that are written into an S3 bucket into one or more of 55 supported languages. You could use this to automatically translate public website assets, for example, so you can communicate effectively with a global audience. You could translate resource files for mobile phone applications, since many users have different language settings on their phones. Or you could translate customer communications to enable analytics to help translate feedback into multiple languages back to one language. Or automate customer support across languages if your customers are based in multiple countries or they speak different languages. Really, there are just many great use cases for this example. In advanced use cases, you could also combine this with AWS machine learning tools for sentiment analysis, or combine with Amazon Recognition to extract the text from images for translation. The key part of the title here is at scale. In an enterprise environment, the application must handle long documents and also large quantities of documents. So let's see how we could develop a scalable translation process. First, an upstream process saves text objects in the batching S3 bucket. The batching function breaks these files into smaller parts, saving these in the translation S3 bucket. This is needed because the translate service limits each individual request to 5,000 characters. When an object is saved in this translation bucket, this invokes the add to queue function. This then writes the message to an SQS queue and logs the item in a Dynamodb table. The Dynamodb table keeps track of the item to know if it's new or it's already translated, so that provides state for all of the items that are flowing through this app. The translator function receives messages from the SQS queue, and it requests translations from the Amazon Translate service. You can control the throughput here by changing the batch size, that's the number of messages fetched by the translation function, and the concurrency of the function. These two levers help smooth out the traffic and control the rate of processing. Once translate returns with results, the function updates the item as completed in the Dynamodb table, and then it also stores the output translation in the results S3 bucket. The translation function gets the original text and submits this to the translate service. To show how this works in code, let's walk through a portion of this function. First, it gets the original text from S3 by using the getObject method, supplying the bucket name and key from the event that triggered the function. Remember, S3 doesn't send the object itself during the invocation process. Instead, it sends a pointer in the form of an event object. Next, it calls a custom function called translateText. This is just a wrapper for the Translate API. Finally, when the translation returns, this is saved to the output S3 bucket as a .txt file using the putObject method. PutObject allows you to set the bucket name, the key name, the body, and the content type using JSON parameters. The AWS SDK is important here since it provides a simple way to interact with AWS services using your chosen runtime. I'm using Node.js here, but you could just as easily use Python, Java, or .NET, for example. This function is the core of this solution. The logic is only focused on processing one event, but the Lambda service handles the scaling as traffic increases. To see the example in your own code and learn more about how this works, visit this URL at the bottom of the slide. In the second example, I show you how you can build an application that converts speech to text. This converts MP3 audio files using Amazon Transcribe. For example, you could use this to transcribe 911 or emergency calls, or analyze customer support calls. You could also provide captions on videos or provide transcriptions for webinars. Any case where you have spoken audio, you could use this to turn it into written text. In advanced use cases, you could create a near real-time transcription for live presentations, or you could combine with Amazon Translate to localize content. You could also enable the search of audio with the Amazon Elasticsearch service. The architecture for this solution is shown here. On the left, an upstream process, such as a call recording system, stores audio data in the application's S3 bucket. When the MP3 objects are stored, this triggers the transcribe function. The function creates a new job in the Amazon Transcribe service. And when the transcription process finishes, transcribe stores the JSON result in the same S3 bucket. So up to this point, that solves the main challenge, converting the audio to text automatically. But now if we wanted to understand the sentiment of what the audio contained, you could also use Amazon Comprehend. So in this case, this JSON object triggers the sentiment function. The sentiment function requests a sentiment analysis from the Comprehend service. Then after receiving the sentiment scores, this function then stores those results in a Dynamodb table. So the last part of this is optional, but it shows how easily you can combine these services serverlessly to solve some fairly complex challenges. You can learn more about this at the URL on the screen. So in the transcribe function, this is how the code works in the Lambda handler. The main purpose of this function is to create a transcription job from the incoming S3 event. First, the function uses Node.js's map function to iterate through the event in case there are multiple S3 events. The main body of the function builds the JSON object expected by the start transcription job method of the transcribe service. It sets the language codes, the media format, and the location of the S3 object. It also provides the output of where the JSON will be stored when the job is done, which is another S3 bucket. The outermost promise.all wrapper allows the function to send multiple jobs asynchronously and then wait for confirmation from the service that the jobs are received. This process is faster than submitting each job one at a time, so it's more efficient if there are many audio files. So in this next example, here's how you can use S3 as a staging area to import data into DynamoDB. This can be used for a general purpose import process for DynamoDB tables, and this approach smooths out the import load to help manage the write capacity units, or WCUs, in DynamoDB. You could also use this to build a CSV import to DynamoDB using on-demand billing if you prefer as well. The entire deployable application is available at the link on the screen, together with more details of how it works. The main architecture looks like this. An upstream process creates a source input data in JSON format and then writes that to the S3 bucket. When the objects are saved, S3 invokes the Lambda function that transforms the input and adds these as messages to the SQS queue. The Lambda service polls the SQS queue and invokes the Lambda function when there are messages. So the function then processes the messages that are in those queues in batches. The function converts the JSON messages into the correct format for the DynamoDB table and uploads this data to the table in batches. So the really important part here is the role of SQS. This buffers the import process, and without it, the writes to DynamoDB would be highly variable if the traffic increased. You can then use the loader function to manage the throughput, which is controlled by the batch size, that's the number of messages fetched from SQS per invocation, and also the concurrency of the Lambda function. The resulting effect is to smooth out the data loading process. In this CloudWatch graph, this is what happens when a large amount of data is stored in the import bucket. You can see that the WCU capacity is fairly stable between 125 and 150 WCUs throughout the import. This is a simple example, but it can be extremely useful if you need to frequently import data into DynamoDB. By using S3 as the staging area and SQS as the buffer, the data is durably persisted until it's imported. Next, let's take a look at workflow management. You can use S3 to initiate step functions workflows. This can be very useful in business applications where logic is triggered by data arriving. For example, the action of saving a signed customer contract from an email could start a work order process. Or receiving a patient medical file in an S3 bucket could initiate scheduling an appointment in another system. Or receiving invoices from a vendor might then start a process that extracts key information using Amazon Textract and then starts a payment process in an accounting system. Again, a full example is available at this URL, which steps through the process in more detail. So in this example, I use step functions to analyze if an uploaded image is a New York State driver's license. In this architecture, an upload process stores data in the S3 bucket. This invokes the start execution Lambda function. This function creates a new execution in step functions using the S3 object as event data. The workflow on the right then invokes the decider function. This uses Amazon recognition to detect the contents of objects stored in S3. This decider function uses environment variables to set the matching attributes. These are driver's license and person in this case. If the S3 object matches those criteria, in other words, recognition finds those attributes in the image, it then triggers the match function. Otherwise, the noMatch function is invoked instead. So it's a simple case, but actually very powerful because you can easily use Amazon machine learning services with just a few lines of code in a Lambda function. Whether there's one image uploaded to S3 or thousands, Lambda and step functions scale up as needed without any changes needed to the code or the logic. To trigger the workflow from the S3 event, you can configure this integration with all the necessary IAM permissions with a SAM template. The start execution function is invoked by the upload to the S3 bucket. This is configured in the events section, which sets up the event source mapping. The step function's state machine ARN is provided as an environment variable. This makes it easy to update which step function's workflow you want to trigger with the Lambda function. The function has permission to invoke that state machine, and the template configures the IAM permissions so that only that defined workflow can be triggered by this function. This is really important because we always want to be following the principles of least privilege. You can use this example code and update the environment variables to make this work for your own applications. It's a really simple way to achieve scalable workflow integrations using the S3 to Lambda pattern. The final example is a searchable enterprise document repository based upon documents stored in S3 buckets. This application can analyze different file formats, so it can analyze and store the contents of PDF files and read Microsoft Word documents that are stored in doc or docx formats. For images like PNGs or JPEGs, it uses Amazon machine learning to detect contents for indexing. The URL at the screen also links to a blog post and repo with the entire solution. So the architecture looks like this. The documents and images are saved in the documents bucket on the left. Depending on the file type, this triggers a custom parser function. For PDFs and docx files, the extracted text is stored in a staging bucket. If the content size is more than 5,000 characters, it's broken into smaller files by a Lambda function, and then saved to a queued bucket. For JPEG files, the parser uses Amazon recognition to detect the contents of the image. The labeling metadata is then stored in the queued bucket. When items are stored in the queued bucket, this then triggers a Lambda function to add the job to an SQS queue. The analyze function is invoked when there are messages in that SQS queue, and this uses Amazon comprehend to find entities in the text. This function then finally stores that metadata in the Amazon Elasticsearch service, and that can help make the indexing data more easily queryable. So this is a highly scalable solution, and it's fairly easy to extend the capabilities for different file formats and for different types of content. So the code in each Lambda function is really very minimal, since the solution uses AWS services to do the heavy lifting. For example, this is the code for detecting the image content in JPEG files. First, it retrieves the bucket name and object key from the S3 event that triggered the Lambda function. Next, it builds parameters for the request made to the recognition service. It sets the maximum number of identification labels to return, and also sets a minimum confidence rating as well. Then it calls the detect labels method of the recognition SDK, which returns a payload. The map function restructures that data to return an array of labels and confidence scores. Finally, it uses the put object method to put this analysis as a JSON object into an output bucket in S3. So within about a dozen lines of code here, this function can analyze the contents of an image and then store the results for further processing. So I've introduced 5 different examples on how to use the S3 to Lambda pattern as a core pattern for building a variety of different solutions for different challenges. Each example has a blog post and a repo, but I also have other videos and resources that can help explain how these work. All of these are available from this URL, s12d.com/S3 to Lambda. There are really 5 aspects of the S3 to Lambda pattern that make it interesting and useful for serverless development. The first is scalability. S3 and Lambda are both highly scalable services, and you can use SQS queues to control the throughput of data in your workflows. This means that your code focuses on the business logic of the application, and the scaling is handled for you. This approach is event-driven. Lambda functions respond to events, so you have custom code responding to a broad range of different S3 events. These can be when objects are created, deleted, or updated, for example. Event-driven applications can be designed to withstand very high levels of traffic and can also be effective for providing near real-time integrations when there are changes in the data. Cost is another factor to consider. You don't pay for Lambda functions when they're not running, so this pattern is an effective way to make sure that you're paying for value. Since you can attribute the cost of the S3 storage and the Lambda invocations, it's also easy to then attribute the cost to your end users. This might be other teams or departments in your company, for example, or it could be your other customers if you're building software as a service applications, for example. And despite the complexity of some of the challenges I presented today, these solutions that I provided use relatively little code. Instead of using AWS services to handle the heavy lifting, that's how they achieve this, by reducing the amount of code that's used. So these light integrations and low-code solutions can make it faster for you and your team to innovate solutions. By managing your deployments with a framework like SAM, or serverless framework, you can go from idea to deployment very quickly. And you can also add features to applications as your customers request more changes. Finally, this approach is extensible. By moving from monolithic apps to microservices that process events, this makes it easier to extend and change functionality or publish events from your applications that other teams can then use to build new features and functions. This can make your development process more agile and more suited to environments where needs change rapidly. So my name is James Bezic, and I'm a developer advocate for the AWS Serverless team. If you have any questions at all, please don't hesitate to reach out to me via email or Twitter. Thanks for listening today, and I look forward to seeing what you build using the S3 to Lambda pattern.